Thank you very much for introducing me. I'm Martin Matušu and I'm from Czech Technical University and slightly from Ostbayerische Technische Hochschule in Amberg-Weiden as well. And together with my colleague from Prague and Amberg, I would like to present this presentation on the topic of fatigue life prediction using the self-heating effect and the LinExp approach, which I will explain afterwards. This is the outline of my presentation. I will briefly introduce you to the production parameters of particularly the SE10 MG aluminum alloy, 3D printed one. Afterwards, I will show you the measuring setup on which we are testing and with which we are measuring the thermal effects during the fatigue tests. I will briefly tell you something about the self-heating effect, although this is the workshop where everybody knows the self-heating effect well. Afterwards, slightly introduce the Fagione method with a focus on the LinExp approach, which we are trying to develop together with our colleagues, and some fatigue curve predictions that we done in this year and the year prior. So what are we dealing with? We are dealing with this aluminum alloy, which is particularly common in 3D printing. It's printed using the laser powder bed fusion technology. In this presentation, I will present 4 different heat treatments. All the specimens were left as printed with no additional machining to the active part and the active cross-section of the specimen. We used a conventional hourglass specimen for the fatigue test, and on the lower part you can see the tensile test specimen, both of which have the diameter in the active cross-section of 9 millimeters. Why am I mentioning the parameters here for the 3D printing is because the printer that we are using is manufactured by GE. They call it a direct metal laser melting, but it's in the family of laser powder bed fusion. They are using a similar concept to the EOS printing printer for the 3D printing metals. They approach the specimen at first with the contour, as you can see here. There are, I hope it's visible on the screen, and it is part of the subsurface, which is printed with the parameters that we call the skin, or they call the skin, and this is printed in each layer. However, the core section is printed with double the layer height and nearly double the laser power. About the heat treatment, what we can see also here is mentioned the trajectory of the gas atmosphere and the rubber coater. This is actually the first platform, the 41 to 44. The heat treatment, where there were 4 heat treatment, or respectively there were 3 heat treatment, one of which was non-heat treated variant. The second of which is recommended by manufacturer, which is 200 degrees, heating up the specimen to 240 degrees for 6 hours, then furnace cooled to 100 degrees, and afterwards is taken out to the ambient temperature. Slightly different approach is to mimic the artificial aging, or this is something similar to artificial aging, although the artificial aging is much more close to 160 degrees, but the 200 degrees Celsius for 2 hours are structurally similar to that. What is interesting and slightly novel approach for the heat treatment is the T300. It's heating up for 300 degrees Celsius for 2 hours and then water quenched. However, it's unique in the sense of this powder, but the EOS EOS printing manufacturer and powder manufacturer recommends this heat treatment for their powder, so it's not that uncommon. For the SN curve, 11 specimen was used for fatigue testing to construct the SN curve, and 3 specimens were delegated for the self-heating tests. Also, at least 3 to 5 specimens were for the tensile testing. In the 2022, we decided to separate the printing platform, as you can see on the left side, where we separated, as you can see by the color, from the left side to the right side. This is something that I would like to warn you about, because there is a slight influence on the printing platform. So for the future printing strategies, or let's say printing approaches, we decided to use a more stochastic approach to divide the platform more randomly on the right side, and I will show you why. Here you can see our measuring setup. On the right side you can see the Amsler resonant pulsator. I think it's a similar machine that Luca showed, as I saw the lower clamps have the similar gearing, so it will be a similar concept as Luca showed. Both of the machines on the left side and on the right side are nearly the same, although they are divided by 20 years. And both of them have 100 kilonewton load cell, and all of the tests in this presentation were conducted under ratio 0.1, so only in tension. For the thermal measurements, we were using Fluke and Flare thermal cameras, one of which at Hamburg and one of which at Prague. On the left side here you can see the tensile equipment. We were using external strain gauges or external tensometer, and on the right side you can see the setup. Although this picture is for Inconel, but it well shows how the setup is, because this is the specimen that is loaded, and this is the specimen that is acting as a, let's say, sensor for the ambient temperature surrounding the testing specimen, as it's better to focus on differences when a difference of temperature than use the actual temperature from the thermal camera without reference. Regarding the tensile test, only this here is only to mention the ultimate tensile strength, as it's further used for the fatigue limit estimation. But to mention, what I would like to mention here is that the non-heat treated variant has, and the T200 has high ultimate tensile strength, and by inducing the temperature from the 240 and 300, you are lowering the tensile properties of the this particular aluminum alloy and lowering the hardness. This particular temperature, close to 300 temperature, it dissolves or decomposes the silicon networking that acts like the brittle material, and lowers the ultimate tensile strength and hardness as well. But this can well transcribe to the fatigue life, as we can see here, because here are the results. I think it's not necessary to explain it, but we were using the end condition for the testing were set to be the 10% decrease or drop of frequency and half a kilonewton difference in the amplitude of load, and the run-out condition were set to 10 million cycles. Now, what I would like to mention here, that the tensile properties well transcribed to the fatigue life properties, as you can see here, because the induced ductility of the T200 shows higher fatigue life in the high cycle fatigue region, and the transition to the fatigue limit. Transition to the fatigue limit, I mean somewhere from 100,000 cycles to 1 million, as you can see here. This is also applicable for the T200 that shows higher fatigue strength in the low cycle fatigue transition region, although 10,000 cycles is hard to say to be low cycle fatigue, but the transition is higher compared to the other ones. Particularly nothing interesting to say about the non-heat treated variant, as it stands out as the worst one. But this is when you're not considering the printing position. If you use fresh powder and more stochastic approach to the printing position, you can see that the nuances between each curve and each heat treatment are much less visible. Particularly for the T240, which is recommended by the manufacturer, and the non-heat treated variant, they are almost negligible. They are visible only in the part of the let's say the run-out condition in this case, and maybe around 1 million cycles. But the results for the T200 and T300 stands out to be the best one and the best option in this case, as it sits right now. But maybe when we will do these tests in the future, the results will be totally different. So this is just a question for the future, Martin. About the self-heating effect. As Luca mentioned, during the cyclic loading of a specimen or metallic structures, usually the loaded sample, as you can see on the left, when the applied force is when there is applied force on the loaded specimen, the self-heating effect or the temperature increase acts in the 3 phases. The first phase is basically described with a rate of temperature. The second phase, which is probably the most important in this presentation, is the stabilized temperature, and the latter phase is the it could be described as the rate of temperature as well. What we were trying to do was to find out the stabilized temperature, to focus on the stabilized temperature for further use. So we designed a step test, but we designed a step test. It means that we inspired ourselves about the step test which was done previously in different papers, although we were using a different materials to set up the how many cycles per the block are necessary to find out the stabilized temperature, as the stabilized temperature is a variable with the amplitude of load. Yeah, as you can see, this is just to show you that the stabilized temperature for the single level test, in single level test I mean from the start of the testing to the failure of the specimen, is the same or similar to the one from the self-heating step test. And here we have a slight problem, I would say. For the T200 and non-heat treated variant, I would say they follow the similar path, although it's not approximated by any curve right now. They follow the similar path. This can be said about the T300, but the T200 somewhat did not, and I would say this is not really similar, and this is going to be visible for the fatigue life prediction as well. What we were trying to use was Fargione's method. Fargione, I think around 2001, postulated that there is something called the limiting energy that can be calculated as an area under the temperature evolution from the start of the test until the failure of the specimen. And this concept of limiting energy is supposed to be a constant value for a variable amplitude of load. This is schematic as I think it should look, and also he postulates that when the summation of the area under the step test is done, this should be equal to the limiting energy from the single level test. So this is the single level test and this is the self-heating step test. Again, I'm focusing on the difference between the loaded loaded sample, temperature on the loaded sample, and the reference specimen, and only on the stabilized temperature. And if we consider the limiting energy as a constant, and we found out the basically the relation between the amplitude of stress and the stabilized temperature, we can proceed with this method to predict the fatigue life for certain amplitude of load. One problem stands out at the beginning, because if we consider the limiting energy as a constant and we take out all the data from the SN curve that I've showed you before, it is not really a constant value. And maybe it's the natural effect of the fatigue life, but what we use here is the average value, because that corresponds to the constant value at most, although the limiting energy decreases with the higher amplitude. So that's only information. I'm missing a graph. But what the problem is, and I've foreshadowed it before, is the T200. The limiting energy from the single level test is nearly double the average value from the self-heating step test, which as I show later is problematic. But why am I saying this? This is a well-known problem, I guess. And for the non-heat treated variant, as I'm showing here, if we use the Faggione method, we would find out that the difference between the self-heating step test as a limiting energy and the single level test, there are not much more differences, although it is more than 20% higher, but it doesn't correspond with the fatigue curve that much. But we can see that the Faggione's method and the regression using the Kohout-Wichert regression, which is the red dashed line, shows good correspondence to the green line, which is the experimentally set up non-heat treated variant. But the problem is that I can start the test wherever I want with the amplitude of testing, and I can evaluate the stabilized temperature much lower than the fatigue limit. So what we need for the Faggione method is the lower threshold. So we need basically a fatigue limit estimate. Luca Corsaro already told you about the TCM method. We haven't applied it yet, but the similar concept of this is going to be presented here. What we were trying to do is not use a power law or a bilinear evolution, as we couldn't basically fit the data as we wanted to find out a good result out of it. So we made a different approach. What we tried to get on was to set the first part of the evolution as first part of the evolution of the stabilized temperature related to the amplitude of load, although here is divided by the fatigue limit, so you can see that there is a visible transition, although this is not going to happen that easily. But the first part is described as a stabilized temperature related to the elastic deformation, although I agree that there is microplasticization around the grains under the fatigue limit. I am aware of that. And the second part we described as a stabilized temperature related to the plastic deformation. And combining these two, let's say, description, we have the whole line, as you can see here. However, we wanted to focus where the transition between the elastic part and the plastic part is visible. This is the ideal result, because we were trying to pinpoint the number one, let's say here, the fatigue limit, and we are really close to it. And how we did it is basically really easy. We took the elastic part, as you can see here, and we retracted the plastic part out of it and find out the maximum value of these differences. And this is where we declare it as the fatigue limit, the point where the plastic damage or the plastic damage value in this case related to the stabilized temperature takes over the linear evolution. We can discuss it further, but this comes with some problems. I tried to compare it with the FKM guidelines, which is quite a useful tool for fatigue life assessment, although it's not directly applicable to additively manufactured materials. I use the FKM guidelines for cast aluminum, which is much more closer than wrought aluminum in my opinion. And what FKM uses is the ultimate tensile strength and RZ, the roughness of the specimen. And here you can see that the linear exponential method, as we call it, is in all of the cases, here it's nearly perfect, but in all of the cases is conservative for the 41 to 44 series. However, the FKM guidelines performs, I would say, well for the heat-treated variants, but for the brittle material of non-heat treated, it does not work that well, because this is, this is basically in the middle of the SN curve, so this is not good. I would try to replicate this approach for the 91 to 94 series as it's supposed to be, and we can see that for the T300 we are close. For the T240 we are slightly over as well for the non-heat treated variant, but the result for the FKM here still shows that it doesn't acknowledge the fatigue limit properly as well for the T200. But however, in general, by using the LinExp approach, we are closer to the actual fatigue limit. Hello, and actual fatigue limit than the FKM guideline. So when we are using the LinExp approach as a lower threshold, you can see the results here. Basically, we are eliminating this the part of the Fagione prediction that are not really related to the SN curve at all, and by this we were able to get really good results, as I would say, and sometimes it's not really conservative, but always it fits in the band of 10% to 90% of probability of failure in this case. And here you can see the FKM guideline. In some ways the FKM guideline works good, but sometimes it does not, which is sometimes problematic. For the T200 and T300 it works as well, and all of these SN curves were set using only 3 samples. So 3 samples for the self-heating step test, out of which we did the LinExp approach, finding out the fatigue limit, and also did the fatigue life prediction by the Fagione's approach. This was also done for the 91st and 91st to 94 series with variable success. 91st series did not work that well, in my opinion. For the 92nd series, we have a really tight spread. Yeah, this is unique for fatigue, I guess. If you look at other publications, this is really good. Basically no outliers. And so we don't fit in the 10 to 90% of probability of failure. For the 93rd, you can see we were able to mimic the SN curve really well. However, the LinExp approach did not work well in this case, and we are too optimistic. For the T300, we are pessimistic, but for any possible construction use of the LinExp approach for the industry, to be conservative is better in this case. To find out if it makes any sense to use this approach, I tried to compare this methodology to setting up the relation between the stabilized temperature in the phase 2 with the amplitude of load, finding out the lower threshold, or in this case, the fatigue limit, and using the fudge-Jones assumption to make the SN curve, or to use only 3 samples for the SN curve. As you've probably seen in the past, some of the research paper tend to make any conclusion out of 3 samples just to make the SN curve. So I'm just asking if it's better to use this methodology or 3 samples for conventional testing for single level amplitude till failure. So what we did was to set up 3 segments, basically. One is based on the maximal stress. One segment is over 70% of ultimate tensile strength. One is between 50 and 70% of ultimate tensile strength, and one which is related to the fatigue limit, or let's say higher fatigue life, which is under 50% of ultimate tensile strength. All this permutation, taking 1 point here, 1 point here, and 1 point here, and make it a Basquin regression out of it, where compared to the one that was produced by the methodology that it was presented prior. And with this approach, we can find out, basically, here you can see the best option for the 3 points, and here you can see the worst option for the 3 points method. And in nearly all of the cases, we are getting better result using the methodology presented in this presentation. For the 41 series, it is nearly 80%. For the 42nd series, you can see a few of the outliers, which may cause a huge problem for the 3-point regression, are working in our favor in this case. And you can see that for the 42nd series, we have a 93% better result, in 93% cases, better result for the cell heating step test approach, as well as for the 43rd series. Due to these points, we were able to get a better result in 100% of cases, although only just, because this is really close to it in this part, according to coefficient of determination. As well as for the 44 series, these points, which are in the region of 800 cycles, 500, 800 cycles, they play a huge role in this 3-point based approach. So to conclude this presentation, the LinExp method, in the case of additively manufactured aluminum alloy, or this powder exactly, works well with a good accuracy, I would say, for nearly all of the series presented in this work. But we are trying to extend this knowledge as much as possible in these days. The comparison was the FKM guideline. It's hard to compare it directly, but for the non-heat treated variant, it works better than the FKM guideline, to be only taking this as a plus point for it, although in some cases it works better as well. LinExp method can recognize better the fatigue limit for the non-heat treated variant. I think with the fudge-Jones method combined with the lower threshold, we were able to mimic or predict the SN curve quite well in all of the cases, except the 91st series, where there were some problems, I think, with the data scatter, so that's quite problematic. And what is the huge claim out of this presentation is that out of all the cases that we are tested, in 75% of the permutation, we were better by using the self-heating methodology presented in this work compared to only 3 samples used for the conventional testing. I would like to thank all of these guys that helped me to make this presentation possible, and thank you for your attention.
So thanks, Martin.